Hi everybody, my name is Lloyd Jones. Thanks for virtually attending my talk about modeling Weibull distributions in brittle solids using two-dimensional bond-based peridynamics. So let's jump straight in and talk about what a Weibull distribution is and why we'd want to model one in peridynamics. So often in peridynamics we're talking about modeling brittle fracture, but in reality, brittle materials often don't have a single fracture strength like where we have our single S0 value in peridynamics. So in real brittle materials, you get these small pseudo-random flaws, and you get stress concentration around these. And instead of being able to just yield and blunt these flaws, in brittle materials, eventually you get frac nucleating on these flaws. So you've got a random distribution of these cracks and flaws in your body, and this leads to a random distribution of fracture strengths for a given brittle material. What we can do is we can empirically fit a distribution to these fracture strengths and use that to predict the fracture strengths of materials in the future. A common method of doing this is the Weibull distribution, where you've got these two parameters to control your Weibull distribution. You've got your characteristic value. In our case, we're using strain, so that's the strain at which the probability of failure is 63%. And you've got your gradient parameter, beta, and that controls the slope of this S-curve. So if you have a larger beta, you'd have a tighter, steeper S-curve. So I want to do just a quick recap on the 1D work on which this 2D work is based. So that was a MATLAB code of a 1D peridynamic simulation of a tensile test, and we would randomly assign strengths to each of the bonds according to a Weibull distribution, and that gives us a really good analogy to Weibull's original weakest link formulation, where he talks about how each piece of material is the strength of that is dictated according to the strength of the weakest part of that material. So we've got this perfect chain that you can imagine in peridynamics. The first problem that we came across there was adjusting the bond distribution to match the size of the overall object distribution. So this is quite a common problem in Weibull sort of problems where you've got different sizes of objects. And what we found is there's a really great analogy for the large object being our overall tensile test specimen, and the small object being each of the peridynamic bonds. So what we found is that we needed to replace the ratio of the size of the large and small objects with just the number of material points that we have in our body. So we found that this almost worked, but we did introduce this sort of slightly difficult problem where we would have tensile test specimens would follow a normal stress strain curve until some point where a bond would break, and that would relieve some stress around the body, and then you would continue to accrue stress before finally fracturing. And we're not getting just a totally clean break, we're getting this sort of breaking in stages. And in order to fix that, what we did was instead of assigning strengths directly to the bonds, we assigned strengths to the material points, and then the bonds would look around them to the material points around them and take their strengths from those values. And what we found that the best way to do that was for the bonds to take on the most extreme values around them, so the very weak values or the very strong values, and that way you've got, rather than a sort of blurred model of strength, you've got very high strength areas and very low strength areas, which we think represents sort of brittle materials quite well. In 2D now, what we wanted to do was use Abaqus to do our peridynamics, which meant using to represent our bonds, we used 1D truss elements, and to represent our material points, we just had nodes with mass elements tied to them. And we utilized Abaqus's ductile damage model. So we essentially have a linear elastic region, and when we get to the point of fracture, we have a very small amount of plastic deformation, like an arbitrarily small amount, 10 to the minus 15 extra strain, and at that point we have fracture. So whereas the relative size of two different 1D bodies is easy to determine, it's a bit more complex in 2D. Real materials scale according to either their surface size or their volume, depending on whether they are something like a glass with a near perfect bulk but flaws on the surface, or a bulk ceramic where flaws have nucleated throughout the body. To represent this, we modified the scaling equation to include either all of the material points or just those at the surfaces under stress. So setting aside our scaling issue for a moment, I want to discuss how we create our heterogeneous strength distribution in 2D. We start with our square mesh of material points before we've even added any bond, and we generate random values for each of them between 0 and 1. We obviously use more decimal places than reality, but we've kept it simple for this graphic. Now let's say we add this bond in between these two material points. We then scan around these two material points in a range of 1 bond's length, and any material point within both of these areas is considered relevant. So we've got any material points that are overlapped by the bond, plus these two that are sort of perpendicular to the bond. You can imagine why, if we say one of these material points contains a large crack, it would make sense that this bond is considered weak. So we're left with these 5 values, and we check which one of those is the most extreme, i.e. the one that's furthest from 0.5, and in this case that is the 0.1 value. We sub that value in as our probability of failure, and depending on our distribution and our scaling method, we've now got a strain which we can use as the fracture criterion for the bond. So here's our simulation setup. It's a simple displacement controlled tensile test, and we've moved the boundary conditions 1 horizon in to avoid any edge effects there. And our default mesh size was 200 by 40 material points, so not very big at all. And our sample size was 30. So for each test, we ran 30 specimens to generate a Weibull curve. So to estimate our Weibull parameters, we first ranked all our specimens by fracture strain, and then estimated probability of failure values based on their rank. We can then plot a straight line through the points on the curve of these two variables, the slope of which is our Weibull modulus. So I talked earlier about surface scaling versus volume scaling, and here are the results of using each. Clearly, surface scaling is a better fit, which isn't a huge surprise given you would expect cracks to nucleate at the surface in this setup. What is interesting is that cracks weren't immediately propagating after initiation. We can see that a distribution of the initiation strains actually fits quite well to the target curve. Since there's more arrest at low strains, the distribution ends up steeper. To fix this, we implemented a method where only the material points at the surface would have random properties and the bulk has a single failure strain. You do end up with a transition zone where only some bonds are connected to the surface and therefore random, and the others are bulk and single failure strain. So here are the results of actually using that method. We end up with an overestimate in both the characteristic strain and the Weibull modulus, but these are actually a result of a single uniform translation to higher strains, mostly a result of that anyway. So you can see that mostly the curve has just shifted to the right as compared to the intended distribution. The actual shape is a reasonable fit, certainly much better than the all surface scaled method. And just to check whether we were just in a lucky space and actually it only fits for that Weibull modulus, we varied that, and we could see that actually quite the opposite was true, and we get a much better fit as we increase the Weibull modulus. The overestimate in the characteristic strain starts to trail off. And while the overestimate in the Weibull modulus doesn't disappear, that's to be expected, because to recreate the same shape at a higher characteristic strain, you actually need to increase that modulus. And we see that we get a fairly proportional relationship between the input modulus and the output modulus. And we talked a little bit about crack arrest earlier, but here's a more sort of quantitative analysis of that. So you can see that we've got the strain at crack initiation on the x-axis here, and on the y-axis, we've got how much strain then continues to be accrued before we actually see fracture of the specimen. And you can see in the all surface method, we've got really quite a spread. We're getting quite a large amount of crack arrest before fracture, even at relatively high crack initiation strains. And when we move to the edge-only method for still keeping the modulus at 6, a lot of that disappears, but you still get, when you get to really low crack initiations, you still get this lots more strain being accrued before fracture. What's interesting is that if you increase the Weibull modulus even just slightly, a lot of that disappears. So what we're seeing is that in these sort of very broad Weibull distributions, the very low strains are very different to the higher strains, and that introduces crack arrest by having areas where we've got very low strain failure, and that's causing the initiation, but then it can't propagate through the relatively high strength bulk. So we wanted to check that our results weren't going to be affected by varying horizon size, and we varied the horizon ratio between 2 and 4. And what we found is actually that for most of our horizon ratio values, the fit was still okay. But as we increased and we got to 4, we could see that there was a significant change in the slope of the curve, and it wasn't associated with an increase in the characteristic strain as we've seen earlier. This is just a genuine steepening of the curve. So you can see it's quite a good fit at the top end, n equals 4, but as you drop down to the lower end, it's miles away. So on this evidence, I don't think we can really recommend using this method with large horizon sizes. So we wanted to check where this error was coming from. So we did the same kind of crack arrest analysis as we did earlier. And you can see that in the larger horizon sizes, particularly m equals 4, you can see that crack arrest starting to happen at higher crack initiation strains again. And that's obviously starting to distort our curve. And that's a real issue, quite aside from the fact that really this isn't the sort of crack behavior that we want to see. We want brittle fracture. So as we get a crack initiating, it should be propagating straight through. So to summarize this work then, first and foremost, when you're modeling Weibull behavior in peridynamics, you've got to get your size scaling right. So you have to scale your distribution of bond strengths depending on either the surface size or the volume size of your specimen. And that will depend on your loading regime and your material behavior. You then want to randomize bond failure criterion according to location. So this is what I was doing by tying bond failure criterion to sort of random values attached to the material points. So rather than having potentially overlapping bonds of different strengths, they're all tied to something which is their location. And then you have your bonds scan around, so they're not just looking at the material points that they're attached to, they're actually looking around themselves a little bit to determine their own failure criterion. And you've got to apply randomization only when necessary. So we had a single failure criterion in the bulk so that we didn't end up influencing our crack growth behavior with this randomization, which is intended to get the crack initiation behavior correct. Unfortunately, there are some limitations, so we need to avoid low Weibull moduli. Beta below 7.5 is where we've sort of drawn our line. That should be okay for most sort of modern engineering ceramics. We're talking in the region 10 to 20 or so. And we've also got to avoid large horizon ratios, so anything n greater than 3. We think there may be some issues from the non-locality interfering with our Weibull behavior there. So thank you very much for listening. Look forward to your questions soon. And all that's left is to just make some acknowledgements to the EPSRC, ICO, CDT and Nuclear Energy and the UK National Nuclear Laboratory, in particular Glyn Rossiter over there, as my industrial supervisors and industrial sponsors. Thank you to both of those organisations for the funding that made this work possible.